So, very good afternoon, everyone. It's our week 11 today. Uh, so, welcome to this live interactive session, a problem solving session. And today we'll be discussing what you have covered in the last week. So you have already covered Nyquist stability criteria and relative stability like gain margin, phase margin, etc. So today we will be solving problems on the same topics, right? But once again, I repeat, so if you're coming to this session, I'm assuming you have gone through the lectures, you have gone through the assignments, you have gone through the notes, at least you have attempted the assignment. At least you have done that. So now let's start. Uh, uh, let me take a problem. So we'll start with a simple question and then slowly build up. And we'll start. And this session we will take in such a way so that you're able to easily solve your assignment, weekly assignment, at the same time learn. Uh, and at the same time, you should be able to solve any of the questions that you might encounter in your exam or in any other competitive exam like it. Okay, so we're given an open loop transfer function g of s h of s, and which is equal to 3 into s plus 3 divided by s square plus 3s minus 4. So we are given this transfer function and we are asked, so this is an open loop transfer function and we are asked to find, the question is find the open loop poles and closed loop poles, right? So obviously, closed loop poles means we are giving feedback, and that feedback is negative. So no need to mention that. But yeah, for the first question I'm mentioning. So the question is, you're given an open loop transfer function. Find the open loop and closed loop poles. Find the open loop and closed loop poles. Okay. Now, how do you solve it? So my g of s h of s is 3 into s plus 3 divided by s squared plus 3s minus 4. So when we solve open loop poles, so we solve the denominator of the open loop transfer function. So my denominator of the open loop transfer function is s squared plus 3s minus 4. This equal to 0 gives me the open loop poles. Okay, so solving it, we can easily write it like this: s plus 4 and s minus 1 equal to 0. It implies my s is either equal to minus 4 or my s is equal to plus 1. So there is one pole which is in the LHP and another pole which is in the RHP. So this open loop system, open loop transfer function is unstable because of the pole in the RHP. Okay. Okay. Now why we are doing it, you'll get to know in a minute. Now so these were open loop poles. Now let's find closed loop poles, CLP. So for closed loop poles, what do we evaluate? We evaluate transfer function, which is 1 plus g of s h of s, and put that to 0, right? So 1 plus 3 into s plus 3 divided by s square plus 3s minus 4 is equal to 0. Okay, so now let's solve it. So you'll get s square plus 3s minus 4 plus 3s plus 9 equal to 0. or I'll get s square plus 6s plus 5 equal to 0, which you can write s plus 5 s plus 1 equal to 0, which means my s is either minus 5 or my s is minus 1. Both the poles lie in LHP, so it means my system is stable. Correct? So my open loop system was unstable, and when I applied negative feedback, my closed loop system became stable, right? Now, in the last week, you studied Nyquist, like we did problems how to draw a Nyquist plot, and today we will see like how we can determine stability from a Nyquist plot, right? So, okay, now let's move towards that part. So how do we stability? One formula is there, NC is equal to Z minus P. So whenever you have to find whether your system is stable or not from the Nyquist plot, so just remember this formula. That is NC is equal to Z minus P, right? So what does it mean? So this NC gives the number of encirclements, gives the number of encirclements of either origin or minus 1 comma 0 point. So for the time being, whatever we are focusing on is minus 1 points, minus 1 comma 0. I'll tell you why. So it gives the encirclement, number of encirclements of the point minus 1 comma 0. So how many times this minus 1 comma 0 is encircled? You have understood, you have learned that already. Now, if I am considering, if my transfer function is g of s, h of s, then I consider the point, the encirclements around minus 1 comma 0. But if instead of g of s, h of s, if I am considering this, like if I am mapping my Nyquist contour, if I am mapping my Nyquist contour to a contour of 1 plus g of h of 1 plus gshs, then you need to check the encirclements around 0 comma 0. So then we check the encirclements about the point 0 comma 0. This is very important. You have questions based on this. So if you are mapping your Nyquist contour to a contour of g of s, h of s, then you need to find the encirclements around the point minus 1 comma 0. Or if you are finding the or if you are mapping the Nyquist contour to a plane of 1 plus gshs, then just find the encirclements about the origin, and that encirclement will give you an idea about stability. So now the next part is, what is Z? Z is number of closed loop poles in RHP. My Z is number of closed loop poles in RHP, and my P is number of open loop poles in RHP. So you know this, that if you have one or more than one pole, if you have any pole in the RHP, then your system is unstable. So with this in from the Nyquist plot, how you will infer that, right? See, when you have a transfer function, I'm asking you find whether the system is stable or unstable. What you do, you find the closed loop transfer function 1 plus GSHS and equate that to 0, find the number of poles. You are done. And this is very simple when you have systems of second order or at most third order. But when your order increases, then you need Route's criteria. And you need Route's criteria, then you solve that, and then you can find this stable, whether your system is stable or not, or how many poles are there in the right half plane. But how you can do the same thing from the Nyquist plot without that much of a hard work, because you're already drawing Nyquist plot to infer some other things, and from the Nyquist plot you can determine stability as well. And how we can determine that? That is given by this formula, very, very important formula, which you will remember. That is NC is Z minus P, where NC gives me the number of encirclements around the point, either minus 1, comma 0 or 0, comma 0, depends on the mapping of Nyquist contour to the GSHS plane or 1 plus GSHS plane, right? And Z is the number of closed loop poles in RHP, and P is the number of open loop poles in RHP, right? So if your NC is equal to positive, if it is coming out to be positive, that means your encirclement is in clockwise direction. You are encircling the point in clockwise direction. So positive sign of NC indicates the encirclement in clockwise direction. And if NC is negative, that means the encirclement is in counterclockwise direction. This is in line with your lectures. Correct? So I have basically revised what you have learned. Now let's move towards questions. Now, this is very interesting question. If you're able to answer these questions, you have learned, you have understood Nyquist stability criteria, you can apply that to solve any question. Now, the same open loop transfer function. So consider the open loop transfer function, G of S, H of S, the same transfer function that we solved as of now, like just before we discussed this. S squared plus 3s plus, minus 4. Now for the same transfer function, one can conclude that the mapped contour, these questions are also in your assignment, that the mapped contour of the Nyquist contour, actually in Nyquist plot we do mapping, so I hope you have gone through the lectures. So the mapped contour of the Nyquist contour in the GSHS, plane encircles the option 1 minus 1, comma 0 point once in counterclockwise direction. Option B, minus 1, comma 0 point once in clockwise direction. Option C, origin, that is 0, comma 0. I'll write origin once in clockwise direction, counterclockwise direction. Option D is origin once in clockwise direction. Now try to understand. So basically this question is a question of Nyquist stability criteria. So you know the formula is NC is equal to Z minus P. Z is the number of closed loop poles and P is the number of open loop poles. So we basically have to find this N. So this N gives me the number of encirclements, and that's what we can see from the options. But there is a twist. So we can easily find this Z, we can easily find this P, and then we can find this N. And from the N, we will decide whether the encirclement is in clockwise direction or counterclockwise direction. See, first of all, if you see from the question, we are given that this mapped contour of the Nyquist contour in the GSHS plane, right? So it is given in the question that we are mapping the Nyquist contour to the GSHS plane. So it means we have to see the encirclement around -1, 0 and not about 0, 0. That means this option and this option goes. So the two options which are saying it encircles origin once in counterclockwise direction or it encircles origin in clockwise direction, that is eliminated. Why? Because we are mapping the Nyquist contour to a contour in the GSHS plane, not in the 1 plus GSHS plane. If it would have been the mapped contour of the Nyquist contour in the 1 plus GSHS plane, then we would have considered this. We would have considered this part, these two options as well, like only these two options there, because the mapped contour in that case was 1 plus GSHS plane. Correct? Now see, this is one thing. So these two options are eliminated. Now we have to see this, like which is the correct option, whether it encircles -1, 0 in counterclockwise direction or it encircles -1, 0 in clockwise direction. See, we have already solved this question. So we found that Z, which are the closed loop poles in the RHP, is 0. See, the closed loop poles were -1 and -5, and the open loop poles were -4 and +1. So open loop pole P, we have solved it. So I'll directly write P is equal to 1 because one of the open loop poles is in the right half plane, which is at s equal to 1. And my Z is equal to 0 because there is no closed loop pole in the right half plane, right? Then what do we get? The value of NC is 0 minus 1, which is equal to -1. Now I told you, whenever the value of NC is negative, that means there is a counterclockwise encirclement. So there is one encirclement, N gives me the number of encirclements, and the sign gives me the direction, right? So there is one encirclement in the counterclockwise direction. So option A is correct. Option A is correct. So Ritik joined late. Let me just revise what we are discussing about so that it is clear for you as well, because we'll be going forward. So basically, we are solving questions based on Nyquist stability criteria. That's what you have understood. That's what you have studied in the last week, and that's what you have questions in the assignment about. So in the Nyquist stability criteria, from the Nyquist plot, you decide whether your system is stable or not. And that is given by this formula, which is this NC is equal to Z minus P. Correct? So what is NC? NC is the number of encirclements of either the point -1, 0 or the point 0, 0. That depends on the mapping we are doing, right? So if we are mapping the Nyquist contour to GSHS plane, then we have to take the encirclement around -1, 0. If we are mapping the Nyquist contour to 1 plus GSHS plane, then we have to take encirclements about 0, 0. And this NC is equal to Z minus P, where Z gives me the number of poles, closed loop poles in the RHP, and P gives me the open loop poles in the RHP, right? If my N is positive, NC is positive, that means the encirclement is in clockwise direction. If my NC is negative, that means the encirclement is in counterclockwise direction, right? So then we took this example. Of an open loop transfer function, and then in the question it was given that one can conclude that the mapped contour of the Nyquist contour in the GSHS plane encircles the, right? Then there are four options. So we are first of all given that the mapped contour is GSHS plane and not 1 plus GSHS. It means the origin is eliminated. Origin is not encircled. We have to see encirclement around -1 comma 0 point. Then the second thing is we need to calculate NC, which is Z minus P. So we have already started our lecture with this question where we had to find open loop poles and closed loop poles. So open loop poles we directly solve from the denominator of open loop transfer function, and the closed loop poles, for closed loop poles we form characteristic equation assuming negative feedback if not given, and find the closed loop poles. So here in this case, we found that we have zero open loop poles. We have one open loop pole in the right half plane. That means my open loop system is unstable. But when I closed it with negative feedback, then I found both the poles are shifted to negative left half plane. It means there is no closed loop pole in the right half plane. So that's what I wrote here. So my Z is closed loop poles in the RHP. My P is open loop poles in the RHP. So I got my P1, Z0, and C is -1. So it means there is one encirclement around the point -1 comma 0. And what is the direction? The direction is counterclockwise because of the -1. So is that clear, Marwan? Okay. Okay, good. So now let's solve one more question. This time I want you to answer. The question is consider an OLTF, that's open loop transfer function, GSHS S minus 7 divided by S square plus 3S plus 2. So this is an open loop transfer function which is given. The question is again similar one. One can conclude that the mapped contour in the Nyquist contour in the GSHS plane, then you have options. It encircles -1 comma 0 point in counterclockwise direction. Option B, it encircles -1 comma point in clockwise direction. Option C, it encircles origin in counterclockwise direction. Option D is it does not encircle -1 comma 0 point at all. So these are the options. Okay. Again, similar question. We have to first identify whether we have to see encirclement around -1 comma 0 or 0 comma 0. Right? If we see the Nyquist contour is mapped to a contour in the GSHS plane, not 1 plus GSHS. So this possibility is eliminated. So we will not see the encirclement around origin, right? Still, we have 3 options left. Okay. Now, how do we solve such questions? We know the formula is NC is equal to Z minus P, where my Z is closed loop poles in RHP and my P is open loop poles in RHP. Correct? So basically what I need to find Z and I need to find P. So let's find P first and then we will find Z. Okay. So okay, let's find Z. So for Z, I will do 1 plus G of S H of S is equal to 0. So 1 plus S minus 7 divided by S square plus 3S plus 2. S square plus 3S plus 2. Okay, equal to 0. Now let's solve it. So I'll get S square plus 3S plus 2 plus S minus 7 equal to 0, or S square 3S plus S is 4S, 2 minus 7 is minus 5 equal to 0. So my equation that I got, the closed loop for the closed loop transfer function, I got S square plus 4S minus 5 equal to 0. So if I solve it, I'll get S plus 5 and S minus 1 equal to 0, which means my S is either minus 5 or my S is either plus 1. So that means my Z is equal to 1. Why? Because there is one pole in the RHP. Okay, now let's find P. So for P, we'll directly solve S square plus 3S plus 2 equal to 0. And I'll get S is equal to minus 1 or S is equal to minus 2. It implies my P is 0 because both of the poles are in the left half. There is no pole in the right half. So what is my NC? My NC is Z minus P, which is equal to 1 minus 0, which is equal to 1, and positive. So it means there is one encirclement of the point minus 1 comma 0 in clockwise direction. Very good. So there is one encirclement of the point minus 1 comma 0 in the clockwise direction. Okay, so I hope you have understood this question. There are a few more questions. Let's solve some more questions. So, but in your assignment, you have similar questions. So just give me a minute. Let's solve some more questions. So in your assignment, make sure you carefully read the questions that whether you have to find encirclements around minus 1 comma 0 or 0 comma 0. Okay, now let's solve one more question. The question is, again, similar question. Okay, similar question. OLTF given is, okay, so OLTF given is G of S H of S is equal to 10 divided by s into s plus 3 into s square plus s plus 1. This is my OLTF. So in the question, it's directly given that find the encirclements NC around -1 plus J0 point. So that means the mapping is done. The mapping of Nyquist control is being done to the plane, which is GSHS plane, right? Because you're being asked to find the encirclements around -1 plus J0 point. So this is the question. That's it, right? So we need to find the encirclement NC around -1 plus J0 point. Well, we know the answer. The answer is very simple. The answer is NC is given by Z minus P. Okay, so we just have to find Z and P, right? So let's find P first. Let's find P. So for P, we'll directly take the denominator of the open loop transfer function, which is basically s plus 3 into s square plus s plus 1. So if you solve this whole, there are 5 roots, if you see. So 2, 3, 4. There are 4 roots of this equation. So if you solve this, you'll get something minus a plus bj. So this is in the left half. It's a complex number in the left half plane. So okay, and this is -3 in the left half plane, and this is 0. So, but when we draw the Nyquist contour, we do not incorporate the region of poles, right? So this we will carefully like bypass these poles. So basically, if we see all the poles are in the left half plane, there is no pole which is in the right half plane. So no open loop pole is in the right half plane. If you carefully solve this equation, it means my P is equal to 0. So that's not a big deal. It's very simple. You can directly solve it, right? You can directly solve it. It's not a big deal. Now let's say Z. For Z, what do you do? For Z, you solve the characteristic equation. So characteristic equation is 1 plus 10 divided by s into s plus 3 into s squared plus s plus 1 equal to 0. Okay, so if you solve it, so we will get a 4th order polynomial like this: s4 plus 4s cubed plus 4s squared plus 3s plus 10 equal to 0. So one way is to directly solve it, but it's very difficult, because it's a 4th order polynomial. If you see the open loop one, that was easier to visualize because it was already factored in a factored form, but now this one is not in that form. Now, how do we proceed? How can we find the roots of this equation? We know we have a method, RH criteria. So we can use RH criteria, and from there we can conclude the number of sign changes will give me the number of roots, a number of poles in the right half plane, right? So let's make route array and do that. So S4, S3, S2. Let's make it in the other page. So my route array will be S4, S3, S square, S1, S0. So it'll be 1, 4, 10. This will be 4 and 3. This will be 16 minus 3 divided by 4. 16 minus 3 is 13. So it's 13 by 4, and this will be 10. And what will this be? 13 by 4 into 3 minus 40 divided by 13 by 4. When you solve it, you'll get minus 9.30. And finally, your S0 is 10. This is it's not difficult to obtain. So what you can conclude from here that there are two sign changes. One is from S square to S1 and other one is from S1 to S0, right? So two sign changes imply there are poles, two poles in RHP. So two closed loop poles in RHP. So that means my Z is equal to 2. That implies my NC is equal to Z minus P, which is equal to 2 minus 0, which is equal to 2. The sign is positive. It means the encirclement will be in clockwise direction. So there are two encirclements. Around the point minus 1 comma minus 1, around the point minus 1 plus j0, two encirclements around this point in clockwise direction. So there are two closed loop poles. So obviously, when we have a pole in the right half plane, it means my system is unstable. That we know. So basically, how do we find that from the Nyquist plot is important, and that's what we have been doing for. That's what we have been doing, right? So is that clear, Marwa? Okay. So basically, it's like this. First, you see what is this order of the system? What is this? What is the type of the system? This is type 1 and order 4, right? So we have type 1 and order 4, and we know how do we draw the polar plot of this type of a system, right? So let me draw first. Like, how will we draw the Nyquist plot? Wait. So type is 1. That means my, okay, let me make it from this color. I'm first making polar plot. So I'll start from somewhere here and order is 4. So my polar plot will be something like this. Wait. And my inverse polar plot will be something like this. Right. Okay, so this is my inverse polar plot, and then I could not draw it accurate. So then I have type 1, and there is one semicircle of infinite radius, right? And your minus 1 comma 0 point, which is actually given after a lot of calculation, it will be somewhere here. So you see there are two encirclements in the clockwise direction. You see in the clockwise direction. So you see this -1, 0, it's encircled. One is this, and other one is this. There are two encirclements. I think this is not covered in your syllabus, and it's not in your syllabus. This is a bit advanced, like because the stability varies because you need to find this point. Sorry, you need to find this point, and it will involve a lot of calculation, right? So I drew an approximate shape of it. Okay. So let's move forward and do one more question. Okay. So let's do one more question. Very interesting question. So now see, the question is, the pole zero plot and the Nyquist plot. The pole zero plot and the Nyquist plot of an open loop transfer function GSHS is shown below. Is shown. Okay, so I'll draw both. So this is your sigma, this is your J omega, RHP, LHP, and your poles are, and your zeros are here. Okay, so this is your pole zero plot, and you have a Nyquist plot, which is something like this. It. The Nyquist plot is something like this. Okay, so this is your Nyquist plot, and I'll just mark the direction of this arrow. Okay, and this is -1. Okay, so this is your Nyquist plot. So it is a real part of, and this is imaginary part. So we are actually seeing the encirclement of -1, 0 point. So that means it's mapped in GSHS plane. So it's mapped in GSHS plane. Now the question is, so we are given a pole zero plot and a Nyquist plot of an open loop transfer function. And the question is asking, from the given plots, we can infer that option A. Both open loop and closed loop systems are unstable. Option B, open loop system is stable, but closed loop system is unstable. Option C, open loop is unstable, but closed loop is stable. Option D is both are stable. Both open loop and closed loop system is stable. Okay. So what you are given a pole zero plot of an open loop transfer function and the corresponding Nyquist plot. So from these two plots, you have to infer the stability of your open loop as well as the closed loop transfer function. This is a very interesting question. Now see. Solution. So if you can see the pole zero plot, all the poles are in the left half plane. So all poles, we don't care about zeros, but all poles, open loop poles, are in LHP. So my P, so NC equal to Z minus P implies my P is 0. My P is 0 because all my open loop poles are in left half plane. It means my open loop system is stable. It means my open loop system is stable. Why? Because all the poles are in the left half plane. And this part is simple, but the other part is tricky. So open loop, so this is eliminated this option. Open loop system is stable. This remains. Open loop system is unstable. It is eliminated. This remains. So our option B and D now remains because open loop system is stable. We can see now the closed loop system is stable or unstable. We have to infer from the Nyquist plot. You see now from the Nyquist plot, you see NC is equal to Z minus P. So my P is 0. So what is now I need to find Z. Z is closed loop pole. So if Z is 1 or 2 or if there is like we need to find Z. If I get Z 0, that means there is no pole in the RHP, then my system is stable. If I get Z1, 2, etc., then it means there are some poles, some closed loop poles in the RHP. Now see, NC is equal to Z minus P. P is 0. NC is equal to Z. So NC I can find from the Nyquist plot. So you see there are two encirclements of the point -1, 0. One encirclement is this, other encirclement is this, and both are in clockwise direction. That means my NC is equal to 2 because they are in clockwise direction. There are two encirclements and both are in clockwise direction. It implies my Z is equal to 2. Z equal to 2 means there are two closed loop poles in RHP. What does that mean? Your system is unstable. Your closed loop system is unstable. So in Nyquist plot, what you do, you take an open loop transfer function and you get things about the closed loop transfer function. You get information about the closed loop transfer function. So that's what we did. So we basically found what are the number of closed loop poles. What is the number of closed loop poles that are in the RHP? That is given by Z, and we found Z, which is given by NC, and NC we found out from the Nyquist plot, and Z came out to be 2. It means there are two poles in the RHP. That means your system is unstable. So which option is correct? This option is correct. That is, open loop system is stable, but closed loop system is unstable. Okay. Is this clear? So I think now you should be able to solve all the questions from the assignment. Okay, all the questions from the assignment related to the Nyquist stability criteria. They are not hard questions. Just ensure the mapping is to 1 plus GS plane or GSHS plane. And again, you have to see whether the encirclement is in clockwise direction or counterclockwise direction, and accordingly you can infer stability. So that's about the Nyquist stability criteria, or the stability from the Nyquist plots. Now there is one more topic that is covered, or there are questions about in your assignment, which is about relative stability, right? So now relative stability. Not going into the details, what is relative stability, etc., etc. As the name infers, it means how much stable or how much unstable your system is. But again, not going into the details, but there are a few terms which I need to revise. So number one is gain crossover frequency. Gain crossover frequency. Number two is phase crossover frequency. Number three is gain margin. And number four is phase margin. So in your assignment, you have questions. Find phase crossover frequency, find gain crossover frequency, find gain margin, find phase margin. We'll revise them and then we will solve questions. Okay. See. So basically, whenever you are, so we are in the frequency domain, right? So we have any transfer function GS, HS. So first of all, we find the sinusoidal transfer function, which is G of J omega and H of J omega. Then we discuss polar plot, Nyquist plot, because this is a complex number. It has some magnitude as well as some phase, right? So if we consider this magnitude of Gj omega, that the magnitude of this transfer function, if we consider this magnitude to be 1, if we consider the magnitude of this transfer function at 1, then the frequency at which this magnitude is 1 is called gain crossover frequency, right? So gain crossover frequency, which is denoted by omega gc, is the frequency at which my magnitude of Gj omega j omega is equal to 1. Very simple, right? So if I am saying magnitude is 1, so in decibels, what will be the magnitude? In decibels, 20 log of 1 is 0. So it means either I'm saying magnitude is 1, or I will say my gain crossover frequency is the frequency at which my magnitude is 0 in decibels. So if I'm talking in terms of decibels, then magnitude is 0 decibels. So when my magnitude is 0 decibels, the frequency at which this happens is called gain crossover frequency. Correct? Now let's come to the phase crossover frequency. So we have phase. So phase, how will I write phase? Phase of Gj omega Hj omega, which is basically angle. So if this angle is minus 180 degree, if this angle is minus 180 degree, then that frequency at which this happens is called phase crossover frequency. So phase crossover frequency is that frequency at which my phase is minus 180 degree. Right? So there are two terms. One is gain crossover frequency. That is when my magnitude is 1, the frequency at which my magnitude is 1. And phase crossover frequency is the frequency at which my phase is minus 180. Now let's come to gain margin. I hope the two things are clear. That is phase crossover frequency and gain crossover frequency. Now see, let's assume the magnitude of my transfer function. let's assume the magnitude of my transfer function at omega equal to phase crossover frequency is x. So let's assume the magnitude at omega equal to omega pc, which is phase crossover frequency. So we will find the magnitude at phase crossover frequency, and that is denoted as x. Then my gain margin is 1 by x. You have to take the reciprocal of that. Again, this is normal magnitude. If I take magnitude in decibels, then my gain margin is 20 log of 1 over x. What physically gain margin is, what physically phase margin is, no need to cover. You have already gone through the lectures, so you know that, because otherwise it will take a lot of time. Just for the time being, remember this. Otherwise, just go through the lectures. That there it will be explained in detail. So actually this gain margin is the amount of gain required to make the system marginally stable. So how much gain is required, that is actually margin. So but for the time being, for the questions, just remember what I'm doing, right? So for gain margin, you have to find the magnitude at omega pc, which is gain, which is phase crossover frequency. If that is x, take its reciprocal, that's gain margin. Take 20 log of that, and that will be gain margin in decibels. Fine, now let's come to phase margin. This is gain margin. Now let's come to phase margin. It's very, very simple. So phase margin means I will calculate phase. So my phase of gj omega, hj omega at gain crossover frequency is if that is equal to phi. So if my angle, if my phase at gain crossover frequency is phi, then my phase margin, is 180 plus phi. That's it. So no decibels, nothing here, right? So your phase margin is 180 plus phi, right? So gain margin and phase margin of a stable system is always positive, right? So I'm talking about gain margin in decibels. So let me write very, very important, which is very, very important for exams point of view, for questions point of view, right? So for stable systems, or note these things. For stable systems, you can visualize it from the Bode plot as well, because when I'm saying gain margin, I'm saying gain margin in decibels. So decibels, you can go to Bode plots, and maybe in the next week we have design, controller design, or lead lag compensator design. If there is something in frequency domain, I can show you that. So for stable systems, your magnitude gj omega pc hj omega pc, this magnitude will be less than 1, and angle will be angle of gj omega pc hj omega pc is greater than minus 180 degree. So in decibels, so my decibel in the gain margin in decibels, so my magnitude is less than 1. For stable systems, my magnitude at omega pc. Why? Because for gain margin, I am calculating magnitude at omega pc, right? Similarly, oh, sorry, here it should be gc, because gain margin, phase margin, I am calculating at gain crossover frequency, right? So, and angle is greater than minus 180. That means my gain margin and phase margin both are positive, so that in decibels, gain margin is positive in decibels actually, and phase margin is also positive. Phase margin is also positive. That is, omega GC is less than omega PC. So in this case, we have gain crossover frequency is less than phase crossover frequency. So, I can show you this from the body plot. Let me make one body plot, and other I'll give you an assignment. Okay. So my gain margin is okay. This is my 0 dB line. This is plus dB. This is negative dB, right? So my gain crossover frequency is less than phase crossover frequency. Let's assume I have a magnitude Bode plot of this and phase something like this. Right now, let's map. See, when my gain is 0, so this is my omega GC. This is gain crossover frequency. That is the frequency when my gain in decibels is 0. And what is my phase? So I have some phase and this margin. So this is minus 180 degree. So this is my gain phase margin. This is my phase margin. And at omega PC, which is omega phase crossover frequency, what is my gain? So this is my gain. So basically, this is my gain margin. That's what I said. This gain margin is the amount of gain required to make this system marginally stable. When my system is marginally stable, then my gain margin and phase margin both are equal to 0. Right? So gain margin and phase margin both are equal to 0. And in that case, my omega GC is equal to omega PC. So that's what I have said. When my gain margin is 0, it means this will be here, somewhere here, right? So that's what's required. So I'm not going into the details. I don't know whether this is covered in your lectures or not, but just for the time being, remember that when you have gain margin below 0 dB, that's actually for sure because gain margin is that's 20 log of 1 by x, which is the magnitude. So when you solve it, it will be negative 20 log of x. So I'm talking about this. So this will be, if you solve it, it will be actually 20 log of 1 minus 20 log of x. This goes to 0. So your gain margin is actually minus 20 log x. So just remember that if your gain margin and phase margin are both positive, then your system is stable. If your gain margin and phase margin are both negative, then your system is unstable. If your gain margin is equal to phase margin, then your system is marginally stable, right? In case of a stable system, your gain crossover frequency is less than your phase crossover frequency. In case of a unstable system, your gain crossover frequency will be somewhere here and phase crossover frequency is here. So your phase crossover frequency is less than gain crossover frequency in case of an unstable system, and in case of a stable system, both are equal, right? So now let's solve some questions which will also help you solve the assignment problems. The question is find gain margin in decibels. So whatever you calculate, just have to multiply 20 log to that. Of a unity feedback control system whose OLTF is given as G of S, H of S is equal to 1 divided by S into S plus 1. Okay, let me solve this for you. So you know gain margin in decibels is equal to 20 log 1 by x. What is x? X is the magnitude of Gj omega Hj omega at omega Pc. What is omega Pc? Omega Pc Omega PC is the phase crossover frequency. It is the frequency when my phase is minus 180. So it is it's my phase. It's the frequency when my phase is minus 180 degree. Correct? So basically I need omega PC. From omega PC, I'll calculate X. From X, I'll calculate gain margin. Correct? But I don't know. As of now, I don't know what is omega PC. Right? So how will I find? So I will equate this. My angle of Gj omega Hj omega is equal to minus 180 degree. And what is the angle? So when will this be? This will be at omega equal to omega Pc. When my omega is equal to phase crossover frequency, then this holds. Now what is the angle? See, this is your transfer function. So I'll again write it again for you. 1 into s plus 1. So this is equal to 1 by j omega into j omega plus 1. So how I can write that? 0 for numerator, then negative for denominator, and j omega. So tan inverse of j omega by 0, that's 90 degree, minus 90 degree for this term, and minus tan inverse of omega pc by 1. Why omega pc? Because we are putting this as minus 180 degree. That's what we know is phase crossover frequency. It's the frequency at which my phase is minus 180 degree. So my minus tan inverse of omega pc is equal to minus 90 degree. This and this goes. My tan inverse omega pc is equal to 90 degree. What does it imply? It implies my omega pc is infinity. My frequency, because tan is infinity, right? So it's 90, tan 90 is infinity. So I have omega pc as infinity. So what is gain margin? Gain now at this omega pc, we will find the magnitude. So what is magnitude of Gj omega? Gj omega Hj omega at omega equal to omega Pc is equal to 1 divided by j omega. So that is omega into 1 plus omega square. So omega is infinity, 1 by huge number. So actually this is infinity. So sorry, 1 by huge number. So 1 by huge number is 0. So it implies my x is 0. Right? So my magnitude x is equal to 0. So that means what is my gain margin? My gain margin is 1 by x. That's infinity. And what's my gain margin in decibels? Again, it's 20 log of infinity. That's infinity dB. Right? So that's how we find. So similarly, you have questions where you are being asked to find whether you are being asked to find the gain crossover, the phase margin. So for phase margin, you need to find the gain crossover frequency, and you need to find the phase at gain crossover frequency, and then just apply the formula of phase margin, and you are done. Right? So now let's solve one more question. First, very conceptual question, and then we'll solve. solve some other questions. So see, the open loop frequency response of a system at two particular frequencies are given. So we have two responses. One magnitude is 1.2, angle is minus 180 degree, and magnitude is 1, angle is minus 190 degree. You have to find the closed loop feedback, the closed loop unity feedback, the closed loop unity feedback is stable, option B unstable, option C marginally stable. Right? So basically we have to identify stability and instability from gain margin, right? So what did I say? If gain margin and phase margin both are positive, then system is stable. So again, this gain margin in decibels. If gain margin and phase margin both are negative, unstable. If they are equal to 0, then they are stable. Then the system is marginally stable. Okay. Now let's see the question. So in the question is given that the response was recorded at two frequencies, right? So one is having the magnitude of 1.2 and a phase of 180 degree. So you know when your phase is 180 minus 180 degree, then the frequency is called phase crossover frequency. So of course you know that this minus 180 phase is coming at omega equal to omega equal to phase crossover frequency, omega PC. Similarly, in the other question, you are given the magnitude is unity and the angle is minus 180 degree. You know the magnitude is unity at omega equal to omega GC, omega gain crossover frequency, right? So correct. So now let's see the first part. The magnitude of GH is 1 by 2 and it's at omega PC. Then what is gain margin? Gain margin is 20 log of 1 by x, 1 by 1.2. If you solve it, you'll get minus 1.6 decibels. Similarly, what is phase margin? Phase margin is 180 plus phi. And what is phi? What is phi? Phi is the angle at gain crossover frequency. So you know phi is given as minus 190 degree. You see, here it's given in the question, phi is minus 190 degree. Means phase margin is 180 degree minus 190 degree. That's equal to minus 10 degree. So phase margin and gain margin both are negative. It means the system is unstable. It means the system is unstable. Okay. So basically, if you solve it, I wrote the approximate values. So if you solve it, you'll find both gain margin and phase margin are negative. That means your system is unstable. That's what was required. Now let's solve one more question. The question is, consider a unity feedback closed loop system whose open loop transfer function. So OLTF is given. That is GSHS. GSHS is given to be 2 divided by S square plus 3S, right? And we have to find gain crossover frequency, right? So let's find gain crossover frequency, because we saw how to find phase crossover frequency and gain margin. Here we will see how to find gain crossover frequency and phase margin. Then we are done, right? So then I think you should be able to solve all the questions. So now let's solve this. What you'll do, first of all, you'll find the sinusoidal transfer function, gj omega into hj omega, which is equal to 2 divided by omega square. J omega square, j square is minus 1. So I'll directly write omega minus omega square plus 3j omega. Okay, so I did nothing. I just put s equal to j omega. Now, at gain crossover frequency, your magnitude is unity. So your magnitude of the transfer function, this is equal to unity. So let's take the magnitude. So if you take the magnitude, it will be 2 divided by under root of omega 4 plus 9 omega square is equal to 1. If you solve it, you'll get omega 4 plus 9 omega square minus 4 is equal to 0. You have a quadratic equation. For example, if you put omega square is equal to u, then it implies you have u square plus 9u minus 4 equal to 0. If you solve this equation, you'll get omega equal to 0.65. Okay, so omega equal to 0.65. If you just solve this equation, you'll get this. You'll get two values. One is negative, one is positive. You'll consider positive. You'll get the value of omega to be 0.65. So you know the frequency at which my magnitude is 1 is gain crossover frequency. That means this is my gain crossover frequency. That is, this is my gain crossover frequency. So again, if I have to calculate the phase crossover frequency, so if in the same question you are being asked to find the phase crossover frequency, what you will do? See, so for phase crossover frequency, you know angle of gj omega p hj omega p is equal to minus 180 degree, right? You'll just find the angle. So you'll just find angle of 2 divided by j omega into 3 plus j omega, right? So what is the angle? The angle is 0 for the numerator, minus 90 minus tan inverse of omega p. This should be p. Omega p by 3, which is equal to minus 180 degree. So if you solve it, you'll get tan inverse of omega p by 3 is equal to minus 90 minus minus goes, you'll get omega p to be infinity. So your phase crossover frequency, omega pc, will be infinity. Then based on what we did earlier, you can find gain margin and phase margin and so on. So that's it. This is your whole assignment. So you have questions based on Nyquist stability criteria. So we did that in detail. So basically, you need to find the number of encirclements around either minus 1, 0 or 0, 0, the origin. That depends on the mapping of Nyquist contour to the plane, either GSHS plane or 1 plus GSHS plane. Accordingly, you decide. And in the second case, then you need to find NC equal to Z minus P, where Z is the closed loop poles, P is the open loop poles. You find them, find Z, find N, and then the direction of N is given by the direction is given by the sign of n, whether it's clockwise or counterclockwise. If it is positive, it's clockwise. If it is negative, it's counterclockwise. And again, you know that any closed loop pole in the right half plane will lead to instability, and accordingly will decide whether your system is stable or unstable. Then we started relative stability, where we saw what is gain crossover frequency, phase crossover frequency, gain margin and phase margin, both in decibels and like normal magnitude. And then you saw that if both your gain margin and phase margin are positive, your system is stable. Gain margin in decibels, of course. And if your gain margin and phase margin are negative, your system is unstable. And if your gain margin and phase margin are equal to 0, your system is marginally stable. And then how to find gain margin and phase margin? You have like you just apply the concept of gain crossover frequency and phase crossover frequency, and just do the calculation and apply the formula for gain margin and phase margin, and you're done. So that's all you have in this week. So now we have only 1 week left, and in the next week probably we have controller design, lead and lag compensator. So I don't know whether the design is based on root locus or gain margin, phase margin, but yeah, that we'll see in the next week. And that will be very interesting. If we have the controller design based on gain margin and phase margin, then we will again see these things in detail in the next week. So if you have any question, please ask. Otherwise, just stop this meeting here. Thank you very much for joining. Have a good day. I'm just ending the meeting for all.